couldn't read you, Joe. I could not read you. Over.
On October 17th, 1982, the Amoco Dome Brazeau well 1312-4812 west of the 5th meridian experienced an uncontrolled flow of gas, or commonly called a blowout. This major well site incident became known as the blowout at Lodgepole. This is the story.
A blowout is simply an uncontrolled flow of gas or oil. That's why this drilling rig is much more than just a machine that drills a hole in the ground. It's connected to a variety of other machines and sophisticated instruments which were designed to help the driller and his crew keep things under their control. They need control of what's going on underground or down the hole. Down the hole is right here. This is where problems can occur. But before we get into those, I want to draw your attention to this. It's called a BOP, a blowout preventer. And because it's going to play a big role in the rest of this story, I want to explain what it does.
This is a simplified drawing of a blowout preventer. It has 3 rams which operate like valves to close off the hole. The top and bottom ones are pipe rams. They are shaped like this to close on the round drill pipe, just like this. The middle rams are called blind rams, and when they close together, they shut off the hole completely. Of course, they can only do this if there's no pipe in the way. And this is called the annular preventer, or more commonly called the bag. The rubber bag is inflated to close off the annulus around the drill pipe, or if required, to close off the open hole when the drill pipe is removed, as in a trip. I want to show you where the blowout preventer stack is positioned. It's indicated in red and sits right on top of the hole. Above the BOP is all the equipment necessary to drill the well. The derrick, hydraulic controls, the rotary table which rotates the drill string, and the Kelly assembly. This assembly is connected to the drill stem and provides drilling rotation, tension, and the circulation system for drilling mud. Drilling mud in deep holes, in difficult circumstances, can be a very complicated chemical solution. This drilling fluid is pumped through the mud hose, around the gooseneck, down the swivel to the drill pipe. The mud circulates down the hollow pipe and through the bit, where it lubricates the rotating bit and carries the rock cuttings up the outside of the pipe, called the annulus, and back to the surface.
Here's what that mud looks like, and it's this, which is every driller's first line of defense against blowouts. This drilling fluid, this mud, you see, does more than just clean out the hole. It also actually pressurizes the hole to prevent gas or oil from coming into the hole. I can show you how this works. Remember your high school physics experiments? If you took a column of water, say this coffee cup, and put a hole down here at the bottom and one closer to the top, see the one at the bottom shoots out much further than the one at the top. That's because down at the bottom, the pressure is greater. It's this pressure at the bottom of a hole that helps stop gas from entering the hole. At least, that's what it's supposed to do. Sometimes gas does enter the system and contaminate the mud. When this happens, it's called a kick. And whenever a kick occurs, the driller has a potential blowout on his hands.
Here's why. When 1 barrel of gas enters the hole at, say, 3,000 meters underground, the gas begins to expand and work its way upwards. At 300 meters from the surface, it becomes 9 barrels. And at the surface, or atmospheric pressure, it expands into 323 barrels of gas. If not controlled, the gas bubble, which displaces heavy mud, lightens the weight of the mud column in the wellbore and could cause a blowout. That's why the neighbor's rig manager and driller, Amoco's own drilling foreman, and in fact all drillers in Alberta, take a special course on how to work this gas out of the system and thus prevent kicks from becoming blowouts. To show how drillers do this, we're going to take another look at the blowout preventer. Normally, when the mud comes back out of the hole, it flows up, past the rams, through the bag, and out to the side where it's piped to the mud tanks. However, when a driller is warned by his instruments and visual checks that a kick has occurred, that gas is in the system, he takes steps to control the expansion of the gas. Remember the bag I mentioned earlier? Well, it is closed off to redirect the mud, which is contaminated with gas, through a relief valve system called the choke manifold. The choke manifold is an array of valves designed to control the pressure and the direction of the flow of the mud returns. From the choke, the contaminated mud goes into a degasser, which does exactly what its name says it does. It separates the gas from the mud. The gas is vented out the top of the degasser to be burned off in a flare pit well away from the rig. The mud falls to the bottom and is returned to the mud system. Meanwhile, the driller has mixed some heavier mud and is pumping this down the hole. Well, it sounds simple enough to me. Yet, every year, there are 150 to 200 blowouts throughout the world. As in any industry, no matter how sophisticated the technology, no matter how well trained the people, industrial accidents can and do occur. The oil and gas industry is no exception, and unfortunately, neither is Amoco. On its Lodgepole site, Amoco was drilling a deviated hole, which means it curved off and away from under the rig like this. This was done because the target zone was under the Pembina River, some 300 meters south of the rig location. The hole was 3,000 meters in depth. That's almost 2 miles deep, and they were in the target zone, where they hoped to find oil. Amoco Canada's drilling manager, Leroy Field, describes what happened at that time.
Well, the third core was being cut in the prospective zone at about 3,000 meters, and everything appeared normal up to this time.
The mud began to splash at the bell nipple, so a flow check was conducted. It appeared that only minor gas cutting was being observed. Shortly thereafter, indications were obtained of increased gas and some H2S. This time the crew got the first indications of a minor kick and some shut-in drill pipe pressure. The constant drill pipe pressure control procedure was being followed when the degasser overloaded about 3.5 hours later, sending mud and gas all over the well site. After repairing the degasser, the crew continued control operations for another 2 hours when another overload occurred. This time, it took 6 hours to repair since the float was jammed and had also collapsed. Repair was hampered by a severe blizzard and the presence of H2S gas. While they were fixing this, the drill pipe parted about 300 meters from surface. They got started pumping kill mud again with the bag and pipe rams holding the pipe and keeping the choke pressure down to prevent hydraulicking. That is, the pipe